Hello there. Tonight we are drifting into the magnificent realm of solar systems, where worlds stranger than you can imagine exist. In a cosmic dance of time and gravity, our own solar system is only one story in a vast library of celestial arrangements, each star surrounded by its own family of planets, moons, rings, and mysteries. Out there in the silent dark are systems of twin suns, molten planets, and worlds floating free in the endless cosmos. This is not just a journey through space. It is a journey through wonder into the hidden architecture of the universe. The things we will discover are not only strange but beautifully real. These faraway systems might challenge what we think life needs, or what a planet even is. If you enjoy these quiet journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here too, one sleepy soul at a time. But for now, just breathe. Let the night sink around you, and allow your mind to settle. Let's begin. Some solar systems have planets orbiting two stars. Imagine sunsets arriving in pairs, and tides pulled by a duet of suns. In circumambulation, a planet loops around both stars at once, threading a path through shifting gravity that looks more like a braided ribbon than a simple ellipse. Stability is possible, because gravity, although complex, can settle into repeating rhythms. When distances and masses fall within certain ranges, the skies would wax and wane in brightness as the stellar partners eclipse or drift apart. From the planet's perspective, painting seasons unlike anything on Earth. Formation studies suggest that dust and ice can still gather into planets, even amid the push and pull of a binary dance, though growth may pause and resume as spiral waves sweep through the disk. These worlds demonstrate nature's flexibility, where physics allows a pocket of order, matter finds a way to congeal. Their existence widens the stage for potential climates, atmospheres, and perhaps someday the chemistry of life. There are solar systems where planets orbit in the opposite direction. Retrograde orbits flip intuition on its head. Instead of following the spin of their star, some worlds swing the other way, as if rewinding the cosmic clock. This backwards motion can arise when a planet is tilted by a passing companion, torqued by a skewed disk, or jostled during youthful gravitational scuffles. The result is an orbital plane misaligned with the stellar equator, sometimes by a little, sometimes by a lot, and occasionally fully reversed. Such geometry reshapes weather and tides, because day and year tug in competing directions. It also records a system's history like a scar, preserving clues about collisions or distant perturbers that once wandered close by. Reading these tilted paths, astronomers reconstruct ancient dramas that ordinary orbits would hide. Each retrograde world is a case file from a celestial detective story, proving that planetary destinies are not always scripted by the neat spin of their newborn star. 1 in every 5 sun-like stars may have an Earth-sized planet. Statistical surveys of dim starlight dips reveal a quiet abundance of small worlds. When researchers correct for vantage point and instrument sensitivity, a striking pattern emerges. Around stars similar in mass and temperature to our own Roughly 1/5 appear to host at least one planet near the size of Earth, and many lie in or near temperate zones, where liquid water could persist under the right conditions. This does not guarantee oceans or breathable air, but it transforms the search from a hunt for rare jewels into a methodical cataloging of nearby possibilities, with each transit measured and each wobble mapped. Candidate worlds step forward for deeper study. Future telescopes will sift their atmospheres for molecules that shimmer with the signatures of clouds, winds, and perhaps biochemistry. The implication is profound. The night is not empty. It is punctuated by countless small shores, waiting for us to learn their weather, their rocks, and their stories. Some planets wander without a star, set adrift by gravitational encounters, or never tethered to a sun in the first place. Rogue planets roam the interstellar dark without a nearby star to warm them. They are lit only by starlight from afar, yet they may carry thick insulating atmospheres, or buried oceans beneath ice, sustained by internal warmth, and tidal stirring during close flybys of other bodies. Detecting these drifters is hard because they do not silhouette a parent star, but careful surveys can catch their faint glow, or the fleeting brightening they cause. When passing in front of distant starlight, their existence shows that planetary birth and eviction are common outcomes of crowded young systems. These lonely worlds turn interstellar space into a subtle archipelago, a scattered fleet of cold islands drifting between the lamps of the galaxy. We have detected solar systems that are almost as old as the universe. Some stars formed when the galaxy was young, enriched by only a few ancestral explosions. Around these ancient suns, astronomers have found the fingerprints of planets. Their chemistry is sparse and heavy elements compared with modern stars, yet still sufficient for dust to clump and build worlds. These venerable systems have quietly orbited for billions upon billions of years, surviving cosmic mergers, tidal shuffles, and waves of star birth. Their planets, if they still possess atmospheres, have weathered epochs beyond any saga on Earth, giving time a chance to test every possible climate tune. They are time capsules, preserving an early recipe for planet formation that challenges models built from our present-day neighborhood. Studying them connects the first chapters of cosmic history with the planetary diversity we see nearby, proving that world-making began soon after the first stars lit up and has been humming along ever since. Planets can migrate from their birthplace. Over billions of years, worlds do not always stay where they first took shape. As young planets exchange momentum with the gas and dust of their natal disks, they can drift inward or outward, sometimes drastically. Later, after the gas clears, gravity games continue as planets tug on one another, trading energy until their orbits stretch, shrink, or even swap places. This slow reshuffling can move an icy giant into a warmer realm or park a giant world close to its star, reshaping the climate of every neighbor. Migration sculpts resonances, clears belts, and can trigger showers of comets that deliver water and organics to inner worlds. It also explains why so many systems defy a simple inside rocky, outside icy pattern. Planetary systems are living architectures, molded by friction and gravity, with final layouts that remember the currents and encounters of their youth, long after the original disk has vanished into starlight. Some solar systems are more crowded than ours. Compact families pack several planets. Inside an orbit smaller than that, the spacing can be tight, yet stable, like pearls on nested strings, because the planets formed together and settled into balanced configurations. In such places, neighboring worlds loom large in the sky, waxing from disks to crescents within a single week. Close quarters amplify tides, stir atmospheres, and create rhythms where conjunctions repeat like a metronome. Crowding does not mean chaos. If masses and distances fall into harmonious ratios that prevent near misses, these systems reveal that nature often prefers efficiency, building many medium worlds rather than a few giants and spreading them across snug lanes. Their climates and compositions may vary dramatically from world to world, despite the shared star offering laboratories where a single sunlight feeds a bouquet of planetary experiments, arranged almost shoulder to shoulder. Solar systems can form with no rocky planets at all. If a disk is poor in heavy elements, or if giant worlds form early and hoard material, the inner regions may never assemble durable rock. Instead, gas and ice dominate, yielding a family of mini Neptunes or gas giants with only small solid cores. In such systems, heat from the star sculpts puffy atmospheres, while distant cold preserves rings and moons carved from icy debris. The absence of terrestrial surfaces transforms everything about habitability and geology. There are no continents to drift, no volcanoes to recycle crust, and no shorelines to cradle oceans. Yet chemistry still thrives in clouds, and on the surfaces of moons and magnetic fields can shield deep atmospheres from stellar tempests. These rockless families demonstrate that planet formation is not obligated to produce Earth analogs. The universe experiments with ensembles, where air and ice are the main stage, while stone plays only a hidden supporting role. We have found solar systems where planets orbit in perfect harmony. Resonant chains lock worlds into synchronized motion, where for every set number of laps by a neighbor completes another exact count. This clockwork keeps orbits from crossing and can persist for immense spans. If no large disturbance arrives, the pattern often forms as planets migrate through the disk, capturing one another into step like dancers adjusting to a shared rhythm. Harmony leaves fingerprints in the timing of transits and the subtle tugs planets exchange, allowing astronomers to weigh them and probe their structures. For inhabitants, if any exist, the heavens would present regular meetings of bright companions predictably spaced like notes in a repeating melody. Such systems show that gravity, when given time and gentle friction, can compose stable music from dust and gas. The result is not rigid but resilient, a natural cadence that reveals the history of migration, written into the beat of the years. Some solar systems are full of planets that are all about the same size. In our solar system, the planets vary dramatically in scale. from tiny Mercury to massive Jupiter. But elsewhere the story can look very different. In several observed systems, all of the known planets are unexpectedly close in size, as though stamped from a cosmic mold. These worlds usually fall between Earth and Neptune in diameter, forming a family of super-Earths or mini-Neptunes lined up in tight orbits. Their surfaces and atmospheres, however, can still differ wildly, depending on their position relative to the star, the chemistry of the protoplanetary disk, and the histories of collision and migration that shaped them. This kind of uniformity suggests formation conditions that distribute material more evenly, or gravitational interactions that keep competing planets in check. Such systems challenge our sense of what is normal. Instead of a few giants and a few small ones, the universe may prefer symmetry. They open questions about whether life-bearing stability might be more common in evenly balanced systems, where no single world dominates the gravitational landscape. There are solar systems where planets skim so close to their stars that metal can vaporize. Some planets race around their stars at distances so short that a full year lasts only hours or days, and daytime temperatures can soar high enough to vaporize iron silicates and other metals. On these ultra-hot worlds, rocky mountains might never form because the ingredients for stone can sublime directly into atmosphere. Winds whip metal vapor from the day side to the night side, where it condenses into glittering mineral clouds that might rain molten droplets back toward the surface. These extreme environments reveal the outer limits of planetary survival under fierce stellar radiation. They also teach us how atmospheres behave when chemistry is pushed far from familiar ranges, creating exotic weather cycles that have no counterpart on Earth. The existence of such worlds shows that planet formation does not avoid the furnace, it adapts to it, building strange spheres that endure in places we once thought entirely hostile to solid matter. We have found solar systems with planets that have no atmosphere. Not every world manages to cling to its surrounding veil of gases. Some planets are being stripped bare by the relentless onslaught of stellar winds, radiation, and gravity. Close-orbiting rocky planets are especially vulnerable, with particles blasted from their surfaces into space until little remains but naked rock. Without an atmosphere to moderate temperature, the day side can bake while the night side freezes. Locked in a brutal tug between scorching light and icy shadow, the lack of air also means no weather, no protection from meteoroid impacts, and no medium for sound to travel. Yet the exposed surface becomes a direct record of the world's history, unclouded by erosion or chemistry. By studying these stark bodies, astronomers learn how atmospheres are lost, what roles magnetic fields play in shielding planets, and how fragile the balance of pressure and temperature can be. Even in their silence, airless planets speak volumes about the struggle to hold on to a sky. Some planets form far from their star, and only later move inward. A planet's birthplace is not always its final address. Far from a star, In the cold outskirts of a young disk, ices and dust can clump more easily, building hefty cores that later drift inward. Like rafts on a river of gas, this slow migration can happen through drag from the disk itself or gravitational nudges from neighboring worlds. A giant planet born in frigid space might eventually settle close to the star, becoming a hot Jupiter that could never have formed in its current. This journey dramatically reshapes the architecture of the system, potentially sweeping aside smaller worlds or stirring belts of debris into chaotic showers. The inward traveler can also trigger resonances that lock other planets into synchronized paths. By tracing these migratory footprints, researchers decode the hidden past of systems that look static today. Planetary placement is a snapshot, not a birth certificate, and many worlds carry the memory of a long inward voyage beneath their clouds. Solar systems can be destroyed when stars become supernovas. When a massive star reaches the end of its life, it can explode with a brilliance that outshines entire galaxies for a brief moment. This detonation, a supernova, unleashes shock waves powerful enough to tear apart nearby planets, vaporize atmospheres, and hurl debris into interstellar space. Even worlds not directly shattered may be sterilized by intense radiation, their chemistry rewritten in an instant. The blast can also carve expanding bubbles through the surrounding gas, triggering star and planet formation in distant regions, while ending it abruptly in the star's own yard. Some planetary fragments might survive as orphaned asteroids or molten cores, wandering the void without a sun. Studying these cataclysmic endings offers a glimpse into the recycling of cosmic material, since the heavy elements forged in the dying star will eventually seed new systems. Solar systems are not eternal, they are chapters in a cycle of creation and destruction written across the galaxy. There are solar systems with planetary rings bigger than stars. Rings are not just for Saturn. Some exoplanets boast ring systems so vast that their total diameter would dwarf even a medium-sized star. These colossal structures may form from shattered moons, captured comets, or leftover debris that never coalesced into a companion. The rings can block light long before and after the planet itself, creating peculiar dips in brightness that first alerted astronomers to their scale. The sheer size of these rings challenges models of stability because such wide disks must resist collapse, spreading or evaporation over millions. Their presence hints at dynamic recent histories, perhaps involving tidal breakups or colossal impacts. If a moon forms within such a ring, it may eventually clear a lane and grow into a fully fledged companion. These oversized halos are reminders that even familiar features like rings can reach breathtaking proportions when gravity and time have the right raw materials. Some solar systems contain moons larger than Earth. Moons are not always minor companions, and a satellite can rival or exceed Earth in size, orbiting a giant planet like a world in its own right. These exomoons may harbor atmospheres, oceans, and complex geology powered by tidal heating from both the planet and the star. Their day length depends on the balance of orbital motion and rotation, creating unusual cycles of light and shadow. Detecting such moons is challenging because their signals blend with those of their host planets. But subtle timing shifts and flickers of starlight offer clues. If confirmed, these giants would expand the concept of habitable zones to include not just planets but their satellites. A moon with Earth-like mass and water could thrive under the protective magnetosphere of a parent planet, benefiting from both stellar and the discovery of such a place would redefine where we look for life and how we imagine homes beyond Earth. We have found solar systems with planets that have no moons at all. Some planets roam their orbits utterly alone, without even a small captured rock to accompany them. The absence of moons can result from violent pasts, where collisions ejected or destroyed early satellites, or from quiet births in regions too barren to build them. Without moons, a planet's axial tilt may wobble more through time, leading to erratic seasons and climate swings. Tides are gentler, reshaping coastlines more slowly, and reducing tidal heating that can fuel geological activity. The night sky would appear stark and empty, with no secondary light to soften the dark. Yet the solitude of these planets offers a pristine laboratory for studying internal dynamics without the complicating tug of a companion. Their very emptiness poses questions about the ingredients and processes that favor moon-making in the great variety of solar systems. Even a missing moon tells a story about chance collision and cosmic scarcity. Some planets have moons that formed before their planet did. In rare cases, a moon may predate the planet it orbits, born as an independent body in the protoplanetary disk, or captured from passing debris long before the main world finished assembling. Later, as material gathered into the planet, gravity pulled the older object into a stable orbit, turning a former wanderer into a satellite. Such ancient moons carry chemical and isotopic signatures that differ from their host planet, preserving a record of earlier conditions in the disk. Their craters and surface layers might reveal impacts and radiation exposure from eras the planet never experienced. This reversal of roles blurs the line between planet and moon, showing that order in a solar system is often a matter of timing and capture, rather than strict hierarchy. Studying these mismatched pairs deepens our understanding of how bodies exchange places and how early formation stages can overlap in surprising ways. The first exoplanets were found orbiting a dead star. Before planets were discovered around sun-like stars, the groundbreaking detections came from a pulsar, the dense spinning core left after a supernova. This stellar remnant emits beams of radio waves with clock-like regularity. Tiny deviations in the timing of those pulses revealed the gravitational pull of orbiting planets, bodies that somehow survived or reformed after the star's explosive death. These worlds endure. Their existence proved that planets can arise in the most unlikely environments, and that planet formation or recycling can happen even after cataclysm. The discovery shattered assumptions and opened the field of exoplanet science, showing that nature writes planetary stories in places far stranger than our gentle solar neighborhood. Every subsequent find traces its lineage back to those first worlds circling a dead sun. Some solar systems have planets that orbit faster than a day on Earth. In some distant solar systems, a planet can complete a full orbit in less time than it takes Earth to experience a single sunrise and sunset. These ultra-short period planets are locked so close to their stars that they race around them in a frantic loop, sometimes in less than 10 Earth hours. Their motion is controlled by extreme gravity and blazing heat, leading to atmospheres that boil away or shift constantly between vapor and plasma. Tidal forces stretch and squeeze them, creating internal friction that can melt rock and drive volcanic activity. If one could stand on the surface, the star might fill half the sky, and the speed of orbit would cause dramatic changes in light across the landscape. Even though the planet often remains tidally locked, with one perpetual day side and one endless night side, these blisteringly fast worlds challenge our expectations about orbital stability and show just how far the universe is willing to push the boundaries of what a planet can endure. We have detected exoplanets that are mostly water. Some worlds beyond our solar system appear to be made almost entirely of water, existing as global oceans without continents or land masses. Their dense pressurized layers may transition from liquid to exotic forms of ice unseen on Earth, such as Ice 7 or Ice X, where water molecules crystallize in cages under unimaginable pressure. Above this watery core lies an atmosphere filled with steam or vapor, possibly enveloped by thick clouds that reflect a high percentage of the star's light, giving the planet a pale blue halo. When observed from afar, these water worlds may experience constant storms, with winds crossing oceans thousands of kilometers wide without interruption. The idea that a planet can form and survive without a significant rocky crust beneath it expands the definition of habitability. If life evolved there, it might have no concept of land at all, thriving in vast underwater ecosystems, completely alien to anything humanity has imagined, where tectonics and volcanism happen. Beneath kilometers of crushing sea, there are solar systems where the planets are made of diamond. Some planetary bodies have been detected with densities and compositions that imply they are rich in carbon, and under the right temperature and pressure, carbon can crystallize as diamond. These so-called diamond worlds likely formed around stars that were themselves composed of carbon-rich material, allowing for carbon to dominate the early planetary disks. As planets cooled and compressed, their interiors may have transformed into vast layers of solid diamond, capped by molten carbon oceans or even carbon dioxide-rich atmospheres. Temperatures on the surface might be sweltering or freezing, depending on distance from the star, but deep below, a glittering mantle of diamond could extend for thousands of kilometers. Such worlds could contain more diamond than has ever existed in the entire history of Earth, turning the concept of treasure into something cosmic. They remind us that beauty, value, and geology take on unimaginable forms across the galaxy, where elements follow universal laws, but the outcomes are anything but ordinary. Some planets orbit so close to their star that a year lasts only hours. In several star systems, astronomers have found planets so close to their host stars that their orbital periods are mere hours long. They complete entire revolutions in the time it takes us to eat breakfast or sleep through a night. These planets are heated to thousands of degrees on their sun-facing sides, causing rock to vaporize and form atmospheres of mineral gases. The skies might shimmer with clouds of silicate particles, and metal could condense and rain as droplets of molten iron. Intense radiation strips these atmospheres away continuously, leaving long comet-like tails trailing behind the planet. As they race around their star, the gravitational pull is so overwhelming that many are tidally locked, with one hemisphere forever exposed to stellar fire, and the other cast in eternal shadow. Their blistering orbits hurtle through warped space-time, illustrating the sheer range of planetary environments that can exist when nature puts the laws of physics to their most dramatic test. We have detected planets as light as cork among the vast catalog of exoplanets. Some are so puffy and lightweight that they would float in water if such a thing were possible on a cosmic scale. These planets have extremely low densities, often less than that of cork, due to their giant sizes and bloated atmospheres filled with hydrogen and helium. They are known as superpuffs or cotton candy planets, orbiting close to their stars, where stellar heat expands their gaseous envelopes to enormous volumes. Despite their impressive radii, their total mass might only equal a few Earths, making them incredibly fragile. The slightest increase in stellar radiation or a close encounter with another object could strip away their atmospheres completely. This strange state challenges our understanding of planetary formation, suggesting that these worlds either formed quickly with vast frozen cores or accumulated gas slowly in gentle environments before drifting inward. Their existence shows how delicately balanced a planet can be, surviving only because the universe allows it, a rare and narrow set of circumstances. Some solar systems have planets far more massive than Jupiter. Jupiter is the heavyweight champion of our solar system, but other systems contain planets that make it look modest by comparison. These superjupiters can be 10 or even 20 times more massive, and yet still qualify as planets, because they are not quite large enough to ignite nuclear fusion and become stars. Their immense gravity can dominate a system, steering the orbits of neighboring planets, sculpting debris belts, and even preventing smaller worlds from forming at all. Their atmospheres may be crushingly dense, filled with exotic chemistry, driven by immense internal pressures, and heat left over from their formation. Some of these giants orbit close to their stars, becoming searing hot and glowing faintly in infrared wavelengths, while others roam far out in the frozen dark with cloud tops colder than any temperature on Earth. The scale of these worlds stretches the word planet to it. The universe permits extraordinary diversity. We have found planets that orbit more than one star at a time, While our Earth orbits a single star, some planets follow paths around multiple suns, circling them as a group. These circumbinary or circumultiple worlds experience complex gravitational ballet, where the star system itself twists, turns, and wobbles. As the planet maintains a wide, stable orbit, the skies of such a world might feature 2 or 3 sunrises and sunsets each day, their positions shifting over time as the stars interact. Temperatures on the surface rise and fall in strange cycles. Shaped by the ever-changing stellar configuration, these multi-star systems reveal yet another way nature builds and balances families of worlds, proving that even under complex gravitational constraints, planets can find a stable home among the stars. In the boundless dark drift ethereal giants, so gossamer light, they could float on water were their cosmic oceans. To cradle these balloon-like worlds, these planets possess densities lighter than cork, their vast volumes swaddled in hydrogen and helium, billowing like celestial cotton candy, orbiting close to their stellar parents, known as superpuffs or cotton candy planets. Though majestic in scale, their mass barely equals a few Earths. Fragile as morning mist, vulnerable to cosmic whispers, the slightest stellar flare or gravitational nudge could strip away their atmospheres, leaving naked cores behind. This delicate existence challenges our cosmic understanding. Were they born rapidly, with frozen hearts, or grew slowly in gentle cradles, before migrating inward? Their survival speaks volumes about universal balance, how celestial bodies persist through rare alignments of circumstance and physics. Meanwhile, in other systems, behemoths roam, planets dwarfing Jupiter, our solar system's giant, these super-Jupiters, massing 10 to 20 times more, yet never crossing the threshold. To stellar ignition, their gravity commands entire systems, sculpting orbits of neighboring worlds, carving debris into precise patterns, sometimes preventing planet formation entirely. Crushingly dense atmospheres bubble with exotic chemistry, forged in immense pressures and primordial heat. Some orbit blistering close, glowing with infrared warmth. Others wander frozen darkness, where cloud tops freeze at temperatures unimaginable on Earth. These extremes stretch definitions, revealing nature's boundless creativity. Within single categories, we find planets dancing around multiple suns, while our Earth waltzes with one. Circumbinary worlds experience gravitational ballets where entire star systems twist and turn in cosmic harmony. Their skies might feature double sunrises and sunsets, painting ever-changing patterns as stellar partners interact. Surface temperatures oscillate in rhythms beyond earthly experience, governed not by single distances but complex gravitational dialogues. These worlds survived chaotic births, where multi-star turbulence could have ejected them into void. Instead, they found equilibrium, circling gravitational centers that drift through space. Like living cosmic entities, they demonstrate how order emerges from apparent chaos, how universal laws weave harmony from complexity. In star clusters, solar systems hide within stellar cities where thousands of stars form in single bursts, packed so densely that night skies glow. With countless suns, here planets endure, despite close stellar encounters that might alter climates or shift orbits slightly. Yet many persist for eons. Their existence proves planetary formation's resilience even in crowded stellar nurseries, where radiation and gravity dance in constant collision. To stand on such worlds means witnessing skies that never know darkness, where cosmic light blazes eternal and planetary life shares space with stellar furnaces. Solar systems face disruption, from passing stars traveling the galactic ocean like ships in vast seas. When stars approach closely, their gravity reshuffles planets, redirects asteroids and comets, sometimes ejects worlds into interstellar space. Such disturbances may send icy bodies plunging inward, bombarding inner planets or pull distant worlds into new orbits, dramatically altering climates. Some planets become lost, slung into void. As rogue wanderers, these encounters seem rare in human timescales, but prove inevitable over stellar lifetimes. The fossil records of such events appear in tilted orbits and eccentric paths, suggesting our solar system's quiet might be cosmic luck. Disruptions remind us solar systems aren't isolated islands, but travelers in dynamic galaxies shaped by unseen encounters. Some planets form in debris disks left by dead stars when stars expire, gently shedding layers to become white dwarfs. They sometimes leave swirling disks of gas and dust and shattered planetary remains. Within these disks, new planets can emerge, recycling materials from previous generations. These second-chance worlds may contain elements forged in dying stars, gaining unusual chemistry, or dense metallic cores. Their parent stars no longer burn like main sequence suns, but glow with residual heat, casting faint light across landscapes that might retain warmth deep underground. This concept expands solar system life cycles, proving destruction can be creation's partner. Reborn worlds inhabit a twilight realm of astrophysics where one cosmic story's end becomes another's prologue. Solar systems sometimes birth from collisions between gas clouds. When enormous gas clouds drift through galaxies, they sometimes intersect with force sufficient to trigger star formation. Collisions compress hydrogen, helium, interstellar dust, causing cloud pockets to collapse under gravity. These compressed pockets become cradles for new stars, each potentially surrounded by planet-forming disks. This dramatic genesis leaves fingerprints on forming systems. Initial turbulence creates planets with wildly tilted orbits, unusual spacing, unexpected chemical compositions. Some planets form quickly, growing massive before chaos settles. Even stars might be born as siblings traveling together, each with entourages of worlds. Such cosmic collisions show star and planet formation isn't always calm, sometimes beginning with interstellar impacts, setting stages for world families. Some solar systems never complete planet formation. Not every protoplanetary disk coalesces into solid worlds. In certain systems, dust and gas remain in suspended swirls for billions of years. These translucent glowing clouds reflect stellar light, revealing stalled planetary birth. Perhaps disks lacked mass or early disturbances prevented larger bodies forming. Sometimes unseen planets shepherd dust into rings without clearing full paths. These half-formed systems act as time capsules, preserving raw ingredients of planet formation. Long after neighbor systems develop rocky surfaces and atmospheric storms, they also replenish galaxies, returning dust to interstellar space, where it might seed next star generations. Studying these lingering clouds helps scientists understand the delicate balance required for planets to emerge, and why some stars never host complete worlds. Some planets orbit beyond their star's light reach. In solar system outskirts lurk worlds so distant their host star appears as bright speck in sky. These planets move through regions where stellar warmth barely penetrates surfaces plunged in bitter cold. Any retained atmosphere may freeze into ice layers, stacking over centuries, until gas slivers remain. Yet some distant giants harbor internal heat, from radioactive decay or birth energy, creating subsurface oceans. Beneath frozen crusts, their slow monumental orbits take thousands of Earth years, making seasons longer than human civilization. These remote worlds remind us solar system architecture extends far beyond cozy zones, where warmth and light create familiar landscapes. In those distant reaches, alien chemistry and endurance replace sunlight as planetary life's ruling forces. We find planets orbiting on tilted axes. Most planets orbit roughly aligned with stellar equators, but some defy this pattern, tilting wildly above or below the stellar plane. Misaligned orbits suggest chaotic pasts involving planetary collisions, gravitational shoves from nearby stars, or warps in early formation disks. For potential inhabitants, seasons would be strange, unpredictable. The star might rise far north for decades, then slowly drift south as the planet continues its tilted path. Climate zones could migrate across surfaces in long cycles, shaping evolution and geography. In unique ways, these skewed orbits are clues to forgotten upheavals in solar system early history, offering rare glimpses into chaotic ballets that shaped worlds long before present paths. Some solar systems host planets with highly eccentric orbits, while Earth moves in mostly circular path. Many exoplanets travel on stretched, elongated tracks, carrying them from blistering proximity to frozen darkness. Eccentric orbits arise from gravitational encounters with other planets, stellar flybys, or leftover formation turbulence. Such planets experience seasons more extreme than Earth's. During orbit parts, they're scorched by radiation, atmospheres swelling with heat storms. Later, retreating into dark, those atmospheres might freeze, creating evaporation frost cycles, reshaping worlds every few centuries. Immense temperature swings fracture rocks, churn oceans, sculpt landscapes with unforgiving power. eccentric planets defy calm orbital rhythms, revealing how gravity's hand can bend and twist. Even the steady heartbeat of years, planets can be torn apart by their star's gravity. When orbiting too close, tidal forces can exceed planetary gravity's strength. Rock and atmosphere layers begin peeling away, forming vaporized material streams spiraling into space. Over time, solid worlds dwindle into remnant cores surrounded by dust clouds and glowing gas. Astronomers detect doomed planets by trails they leave behind, like cosmic breadcrumbs, marking final journeys. Shredded worlds may become rings, dust belts, or fuel future planets. And saying the process isn't quick, taking millions of years for planets to fully unravel under stellar pull. Yet results remain constant. Reminders that gravity gives and gravity takes away, sculpting planetary fates with same quiet certainty, guiding galaxies. Some solar systems contain asteroid belts vaster than ours. Our asteroid belt, between Mars and Jupiter, seems modest compared to systems featuring belts hundreds times more massive, filled with objects ranging from dust grains to mountain fragments. These colossal belts may be wreckage of never-formed worlds, or remains of past collisions, shattering planets to pieces. Sheer debris volume can fill nearby planet skies with glittering shards and fire streaks, especially in young systems where collisions frequent. Such belts serve as archives, preserving original disk chemistry. Long after larger bodies evolve, they may seed inter-planet life, delivering water and organic molecules during heavy bombardment periods. These oversized stone and ice rings reveal unfinished planet-making business where creation leftovers linger, participating in cosmic stories for eons. Some solar systems possess multiple habitable zones. The habitable zone, usually imagined as single band where liquid water can exist on planetary surfaces. But some systems host multiple such regions. Stars with broad temperature ranges or binary systems with dual heat sources can create overlapping or distinct habitable bands. One region might support rocky planets with temperate conditions, while farther out, gas giants with watery moons could harbor life. Multiple habitable zones expand potential biosphere canvas, suggesting life could arise in more places than previously thought. These zones shift over time as stars grow hotter or dimmer, giving planets temporary windows where conditions align perfectly. Multiple habitable bands make these systems rich exploration targets, hinting at nature's adaptability when given proper conditions in multiple neighborhoods. Habitable zones migrate as stars age. Stars change over billions of years, growing brighter and hotter. While burning through fuel, this evolution causes liquid water regions to drift outward. Once temperate planets may become too hot, while farther frozen worlds might thaw into new oases. Such planetary migrations through habitability can create life epochs, separated by long dormancy ages. For Earth-like worlds, habitable windows are temporary, slowly edging toward futures where oceans boil and only poles remain cool. Shifting zones reveal habitability isn't static, but moving target, shaped by stellar aging and planetary endurance. Understanding this dynamic helps scientists search for life on planets only now entering golden ages, even if they once lay beyond warmth and water reach. Some solar systems form in star-forming nebulae in galaxies' brightest regions. Vast nebulae glow with ionized gas and starlight. These stellar nurseries birth solar systems in numbers as gas filaments collapse into star clusters, each gathering dust and ice disks. Intense radiation from nearby massive stars can sculpt newborn planets, stripping atmospheres or igniting chemistry. Impossible in quieter neighborhoods. Planet skies in such places would blaze with shifting red-blue clouds lit by enormous sun's ultraviolet glow. Each world carries birthplace imprint, rare metals from ancient supernova, complex molecules from earlier star generations, and scars from radiation storms battering early surfaces. Nebula-born systems remind us planetary creation isn't always gentle, sometimes occurring in giant shadows under skies burning. With thousand-star fire, solar systems may begin forming before stars fully birth, before stellar cores ignite into steady nuclear fusion, while still gathering mass from surrounding clouds. Their gravity can already shape swirling dust and gas disks. In early phases, tiny grains collide and stick, forming pebbles, then boulders, eventually planet seeds, even as protostars flicker and contract. These planetesimals carve disk lanes, accreting material, casting future world shadows. In this twilight period, before stars settle into stable burning, properties like disk temperature, magnetic turbulence, and chemical gradients can predetermine planet types. Rocky, icy, gaseous, or none at all, solar system stories begin, but with quiet choreography of dust, spirals, and visible forces. By time stars fully awaken, their planetary children may already be maturing. Some solar systems align perfectly. Others appear chaotic. Certain systems possess serene symmetry, all planets orbiting neatly in same plane, aligned with stellar spin. Others are wild mosaics of tilted, twisted, looping paths, defying tidy logic seen in our neighborhood. In chaotic systems, planets may orbit at sharp angles, circle above or below stellar equators, or move retrograde against stellar rotation. These patterns often arise from ancient upheavals, giant impacts, gravitational encounters with neighbor stars, or turbulent gas disk collapses that never fully settled. Results are cosmic memory snapshots, imprints of every force that shaped systems. Studying both orderly and unpredictable teaches astronomers nature's blueprint allows beauty in balance and disorder, proving harmony and chaos, both part of cosmic design. Some planets never finish forming. Before stars burn away material, planet formation races between growth and loss. Not all participants reach finish lines. Around some stars, young stars, intense heat and radiation burn away protoplanetary disk wisps before planetesimals fully assemble into planets. unfinished worlds remain as massive asteroids, scattered rubble piles, or moon-sized bodies, too small to round into spheres or hold stable atmospheres. Their surfaces bear collision scars, never smoothed by gravity's gentle hand. Long after gas disappears, these fragments drift silently, reminders of what might have been had time stretched further. Studying incomplete planets offers insight into delicate balances of timing and environment. In planet formation, even most promising beginnings can be cut short when young stars turn fierce too quickly. We've detected solar systems forming around baby stars. Protostars glow faintly, while gathering mass, evolving toward main sequence. Around them, dust and gas disks whirl in thick, luminous bands, warmed by growing stars' soft energy. In these warm, churning disks, astronomers detect distinctive gaps and rings marking planet formation's early stages. Planets here might still be molten, layered with hot ices, or wrapped in thick nebular atmospheres. Entire systems move as creation portraits, dust grains spiraling inward, ice giants carving glowing trails, gas nodding into weather, ocean, sky futures. Observing baby systems resembles watching time lapses of our solar system's youth, revealing not just what we are, but what we were. Every telescope shutter click captures cosmic childhood pieces we can never relive. Some solar systems show signs of full planetary destruction. In certain star systems, astronomers find overwhelming evidence that planets once existed but exist no longer. Clearest clues are glowing metallic dust rings, polluted white dwarfs filled with silicon and iron, or vaporized rock clouds orbiting too close to stars to be natural. These are scattered remains of worlds ripped apart by tidal forces, obliterated in stellar expansion, or shattered by violent collisions. Even moons or minuscule pebbles may still be present, silently tracing outlines of once thriving world systems. Planetary destruction on such scales reminds us solar systems are fragile, temporary arrangements. Their stories include not just birth and evolution, but they contribute material that may someday birth new planets, reincarnating atoms in next star generations. Some systems form in galactic cores. Galactic hearts aren't empty, but densely packed with stars, gas, dust, immense gravitational forces. Amid this chaos, solar systems can form. Though environments differ dramatically from ours, stars born in galactic cores may be bombarded by radiation from nearby supernova or jostled by gravitational tides from passing stellar neighbors. Disks forming around these young stars are rich in heavy elements, forged by previous generations, allowing planets to form quickly. Often with high metallic composition, these planets, if surviving long enough, might develop unusual atmospheres or compressed cores due to frequent gravitational disturbances. Life, if arising, would adjust to skies filled not with isolated light pinpricks, but almost solid walls of nearby suns. Galactic core solar systems remind us planet formation is possible everywhere, even in busiest, noisiest cosmic city corners. Some planets possess atmospheres made entirely of metal vapors. On certain ultra-hot exoplanets, temperatures are so extreme that metals like sodium, magnesium, and even iron vaporize into gases. These metallic atmospheres shimmer like liquid mirrors, reflecting and refracting light into brilliant spectral lines, detectable from light years away. Winds on such worlds might flow at thousands of kilometers hourly, carrying metal vapor from day sides to night sides, where it condenses into glittering clouds or rains molten droplets. Skies here are alien in every sense, with lightning storms crackling through metallic haze. No oxygen or nitrogen breath to soften air. These shimmering worlds push atmosphere definitions to extremes, reminding us what seems unimaginable on Earth may be ordinary elsewhere. In space, even air can be forged from fire and metal. We found planets that may rain glass or rubies. Some planets possess atmospheres rich in exotic silicates and mineral compounds that condense into crystals rather than water. On these worlds, colossal winds can hurl molten particles high into air, where they cool into shimmering glass grains, or precious gemstones like corundum, the mineral behind sapphire and ruby. As gravity takes hold, these crystals fall like colorful rain, scouring surfaces, or bouncing across roiling oceans of liquid metals. Fierce winds, extreme temperatures, unique chemistry combine, creating landscapes sparkling, not with frost or dew, but shining treasure, torn from skies. On such planets, storms can become legends, turning weather into weapons or wonders. These places remind us beauty and danger often walk hand in hand through cosmos, turning known elements into art beyond earthly imagination. Some solar systems contain tidally locked planets. Tidal locking occurs when planetary rotation slows to match orbit, leaving one side forever facing star, the other plunged in constant night. This is common among worlds orbiting close to dim, cool stars, where gravitational tides act quickly. Daytime hemispheres bake under unending starlight, while night hemispheres chill near absolute zero, forming planets cut in two by shadow and twilight bands between. Strange weather patterns swirl, transporting heat and gases in endless cycles. Oceans might cluster along these terminator zones, while life, if existing, would adapt to skies where stars never rise or set. Tidal locking challenges traditional habitability pictures, but recent models show with proper atmospheres or oceans, such planets could support stable climates, even thriving ecosystems. Not all dual worlds are lifeless. Some simply bear climates shaped by relentless starlight and eternal night. Some planets spin so fast they nearly break apart. Few exoplanets rotate so rapidly their equators bulge outward, stretched by centrifugal force to instability brink. These planets may complete full rotations in just hours, whipping atmospheres into cyclones, flattening shapes into oblate spheroids. At such speeds, gravity pulls harder at poles than equators, creating worlds perpetually, balancing on chaos edge. Each revelation about exoplanets expands not just cosmic knowledge but philosophical understanding of our place in universe and in infinite possibilities for existence itself. Some planets spin so fast they dance on the edge of destruction. Their furious rotation creates wild differences in atmospheric pressure and temperature. If they spun any faster, they would fling material into space or tear apart entirely. The forces at play create firestorms, shock fronts, and extreme auroras, painting their skies in ways we cannot easily imagine. Their dizzying rotation is a clue to their youth, or their violent past, perhaps a legacy of collisions or migration that left them spinning like cosmic tops. These worlds are testaments to the boundaries of planetary endurance, where physics writes poetry at the edge of destruction. Some planets reflect so much light, they shine like mirrors. Far from our skies, a handful of worlds shimmer like polished metal, returning an astonishing fraction of the starlight that falls upon them. Their brilliance can come from bright cloud decks seeded with tiny crystals, from vaporized minerals that condense into reflective hazes, or from surfaces glazed into glass by relentless heat. This high reflectivity turns them into beacons that rise and fall in brightness as clouds migrate and storms breathe across the day side. That flicker is a gift to observers, since changes in glow reveal wind speeds, cloud heights, and even hints of chemistry without a single drop of landfall. Some of these gleaming planets circle so close to their suns that the mirror is a living thing, constantly remade as minerals boil travel on supersonic winds and settle again as glittering frost. Others are cooler, but mantled in ices or salts that keep them luminous. Each one is a natural signal flare that tells us what its sky is made of. We have found planets that float in almost total darkness. Astronomers have uncovered worlds that travel through space without a parent sun, set adrift during turbulent youth, or never bound in the first place without nearby starlight. Their landscapes are lit only by the faint red warmth of their own interior heat. Any atmosphere becomes a slow blanket, holding what little energy remains while the surface freezes into plains of dark ice. Where pressure grows, great buried oceans may survive under shells of frozen gases kept liquid by the steady murmur of radioactive warmth in the rock. These planets are nearly invisible, yet they reveal themselves through brief gravitational lensing events when their mass bends distant starlight for a moment and then slips away. A few are warm enough to they are reminders that planet making is messy and that the galaxy is sprinkled with lonely worlds that carry their nights with them. Some solar systems have planets made of exotic matter. Most planets we know are mixtures of rock, ice, and gas, but theory allows for objects stranger than anything in our solar system. If a collapsing cloud carries unusual chemistry or is exposed to extreme pressure for long periods, matter can settle into states that seldom appear elsewhere. Deep interiors might become crystalline carbon on a colossal scale, or metallic hydrogen that behaves like a sea of electrons. Some scenarios even predict ultra-dense forms of matter that pack more mass into less volume than any ordinary planet could sustain. These bodies would be small, heavy, and fiercely gravitational, with surfaces that swallow meteorites without a trace. They might form in regions seeded by ancient supernovas or near compact stars where tides and pressure drive matter into extremes. We have not yet visited such places, but their gravitational pull and the way they affect nearby starlight hint that nature's playbook for building planets is broader than our local sample suggests. We have detected signs of planets being consumed by their stars. A star that swells in old age can swell enough to touch a nearby world. When that happens, gas from the planet spirals inward and leaves fingerprints in the star. Astronomers see sudden enrichments of elements like lithium and iron in stellar atmospheres, patterns that do not arise from normal stellar cooking. Some stars also spin faster than expected for their age, as if a recent meal added angular momentum around white dwarfs, which are the embers left after a sun-like star expires. Heavy elements appear in the thin stellar surface, even though they should sink quickly. The only plausible source is a steady drizzle of planet crumbs and asteroid dust falling in from disrupted infrared glows from hot debris rings and tiny dips in starlight that repeat irregularly complete the picture. What we witness is not a single catastrophe, but a menu of endings, each showing how gravity eventually collects what it once allowed to wander. Some planets have magnetic fields far stronger than Jupiter's. Giant planets with roaring interiors can generate magnetic fields that dwarf anything in our solar system. Fast rotation and deep layers of conductive fluid act like a dynamo, turning internal heat and motion into vast invisible. These fields trap charged particles and funnel them into poles, where auroras bloom large enough to outshine the host star. In radio light, space around such a world becomes a fortress of magnetism, with bow shocks in the stellar wind and tails that stretch for millions of kilometers. The strength of the field hints at the constitution of the interior, perhaps metallic hydrogen, under crushing pressure, or salty oceans wrapped around super-Earth cores. When a planet with a powerful magnetosphere skims close to its star, magnetic interactions can even heat its upper atmosphere and change the chemistry of its auroral glow. By listening for those radio murmurs and watching for ultraviolet flashes, we learn to weigh the hearts of distant worlds. There are solar systems with more than one asteroid belt. Beyond many stars lie not one, but several belts of leftover building blocks, stacked like nested rings. Each belt carries a different temperature and composition, with warm inner debris, rich in rocky fragments, and colder outer regions stocked with ices and organics. Gaps between belts are not empty mistakes. They're often the signature of unseen planets that have quietly swept lanes clear or locked dust into resonant patterns. The structure of these belts reveals a history of growth and interruption, of worlds that formed quickly and others that stalled. Collisions within the belts grind larger bodies down into fine dust, which shines in infrared light and outlines the architecture like chalk on a blackboard. When a young system is especially active, that dust brightens and fades, on human timescales as smash-ups come and go. In older systems, the belts persist as archives preserving a record of the materials that once circled far more thickly. Some solar systems form around stars, too small to be seen with the naked eye. Tiny stars cool enough to appear as red embers on the cosmic stove are everywhere, and many of them host planets. Their disks are smaller and longer-lived than those around bright suns, which give small worlds ample time to grow. Orbits snugly close to these stars receive present levels of warmth, even though the stellar light would look dim and red to human eyes. Flares can be frequent in youth, but over long spans the steps toward stability arrive, and atmospheres that are dense or magnetically shielded can endure. Because these stars are faint and common, their planets make up a large share of the habitable real estate in the galaxy. Transits repeat often, which lets observers map atmospheres, seasons, and sometimes weather. From a surface bathed in crimson, the possibilities that gather around small fires are not small at all. We have observed planets that orbit inside stellar winds. Every active star breathes a river of charged particles that flows outward in all directions. Some planets circle so near to that breath that their skies are carved by constant particle storms. At the boundary where the wind meets the planetary field, shock fronts form and accelerate particles into auroras that encircle entire hemispheres. The wind strips light gases, sculpts plasma tails, and can even induce electric currents that heat the upper atmosphere from within. These environments are harsh yet informative. The way a planet resists or yields tells us whether it has a global magnetic field, how dense its air might be, and what volatile elements are present. As the star cycles between quiet and active, the planet's response changes rhythmically. To watch such a world is to see whether that begins at a sun and ends in a sky, a complete circuit from stellar heartbeat to planetary glow. Some solar systems have planets with comet-like tails. Not all tails belong to comets. Some close-in planets shed gas so quickly that a long stream trails behind them, curved by orbital motion and pushed outward by the pressure of starlight. The tail can be made of hydrogen, torn from an upper atmosphere or heavier vapors, from rocks that evaporate under fierce heat. When the planet passes in front of its star, the tail starts blocking light before the planet arrives, and keeps blocking light after it departs, creating a transit with a drawn-out entrance and exit. Different colors of light are absorbed at different points along the stream, which lets observers separate the ingredients and watch how they change with time. Tails can break into clumps, fade and regrow as the stellar wind changes. There are living records of escape, showing how a world loses breath to its sun and how quickly a fragile sky can thin. We have found planets that orbit black holes. Worlds can circle the darkest objects in the cosmos, bound not by warmth but by gravity alone. In such a system, daylight would come from a distant companion star or from a glowing disk of gas, spiraling toward the black. Orbits must be wide enough to avoid destructive tides, yet close enough to remain bound against the tug of passing stars. Detection is difficult, so the evidence arrives in pieces. Subtle gravitational lensing events hint that a compact massive center carries a lighter companion, flickers in the light of accretion disks, suggest an unseen planet shepherding gas into waves. The physics is stark, but not hostile to stability. If conditions are calm and radiation levels are modest, moons and atmospheres could persist for very long times. In these remote precincts, the ruler is gravity itself, and a planet survives by learning the quiet geometry of a deep well in space-time. Some planets never experience night at all. On certain worlds, the concept of night does not exist. These planets either rotate so slowly or are tidally locked to their stars, resulting in one hemisphere bathed in perpetual daylight, while the other is frozen in endless shadow. On the day side, the sun never sets, climbing only slightly across the sky as years pass, blazing down with unbroken radiation. Temperatures climb to extraordinary levels. Towering clouds of steam or dust rise from the surface, and winds swirl constantly in convection loops. Vegetation or life, if it ever evolves, would grow without rest. Under blinding, relentless light, the twilight zone between the two extremes might hold the only refuge, a thin band where the heat of the day and the cold of the night find a fleeting balance. These worlds show that a planet's rhythm, its breathing in and out of light and shadow, is not universal. Some live an eternal day, never knowing the calm of darkness. There are solar systems with planets that glow from their own heat. Some young or massive planets radiate so intensely with internal heat that they shine faintly in infrared or even visible light. These glowing worlds may still be cooling. From their violent birth, their interiors churning. With molten rock and compressed metals, others generate heat through tidal friction, pulled and squeezed by the gravity of nearby giants. In a perpetual cycle of flexing and release, their energy oozes outward, creating surfaces that may shimmer with molten lakes, glowing clouds, or burning atmospheres rich in vaporized elements. From afar, these planets appear like miniature stars. In time, they may cool, darken, and settle into familiar silence. But for millions of years, they blaze with the fire of youth. Their heat is a reminder that planets are not merely dark rocks circling suns. Sometimes they are suns in miniature, carrying their own inner flame. We have detected solar systems that are still swirling with dust. Many solar systems never completely clear. The chaos of their childhood, long after planets have formed, the space between them can remain filled with clouds of microscopic grains, shattered fragments of comets, and shattered rock that reflect starlight in a glowing haze. These dust clouds glow in infrared wavelengths, outlining lanes and arcs, sculpted by hidden worlds or by the gravity of fast-moving giants. In young systems, the dust is thick enough to block or scatter visible light, turning everything into a warm, smoky fog. It can also reveal clues about ongoing collisions, planetary migration, or the birth of moons. In older systems, the remaining dust is a faint echo of earlier violence made visible only when a nearby star shines through it. These swirling remnants show us that planetary architecture is never truly finished. It settles, shifts, and sometimes grows messy again as worlds collide, decay, or keep forming from dust. Unclaimed planets can form in the shadow of giant stars. Massive stars burn hot and fast, radiating so fiercely that nearby materials are stripped, melted, or pushed away, and yet, in the shadows cast by their enormous disks or in stable eddies behind dense clumps of gas, planets can still form, protected from the worst radiation. Silicate grains cling together, ice coats tiny pebbles, and larger bodies slowly take shape even as the parent star burns, millions of times brighter than our sun. When the giant finally explodes, in a supernova, the shock wave may strip away atmospheres or blast the forming worlds with cosmic rays, but some planets can survive, shielded by timing or orbit, carrying within them materials enriched with heavy elements forged in the star's final moments. These worlds are born in danger, but what remains can be more exotic, more metal-rich, and more dynamic than anything our own system has to offer. They are literal survivors of stellar fire. Some solar systems are slowly being eaten by their star's radiation. In certain systems, the star emits so much high-energy radiation that its planets are stripped of their atmospheres, atom by atom, over billions of years. The gas that once formed thick skies begins to erode, rising into space and drifting like cosmic smoke. Lighter elements escape first, leaving behind heavier particles that may clump or fall toward the planet in strange rains. Some of these worlds shrink, visibly losing mass and changing density, as their surface is sandblasted by invisible storms of ultraviolet and charged particles. In extreme cases, the entire planet may vanish, leaving only a rocky core or a sparse ring of dust in its place. These erosive solar winds turn planets into slowly fading memories, their substance carried outward to seed space with fragments of ancient ground and sky. The universe holds no permanence, not even for worlds. We have found solar systems that contain interstellar visitors. Sometimes a frozen wanderer is captured by the gravity of a distant star, trapped in an orbit and adopted into a new family of worlds. These visitors likely formed around other stars, but were flung outward by violent early events, traveling alone for ages. Before being pulled in by another sun, their orbits are often stretched and angled strangely like relics from another story, dropped into unfamiliar company. Their composition may reflect a different chemistry, revealing rare metals, complex ices, or isotopes not found in the native solar system. Long-term studies may show whether they become stable or whether they will be flung away again after a few million years. Their presence reminds us that the line between stars is porous. Solar systems do not own their objects permanently. Space is a place of exchange where even planets can change homes. Some solar systems create giant planets in just a few thousand years. The standard picture of planet formation includes slow accumulation, with gas giants taking millions of years to emerge. Yet in some systems, these colossal planets form in just a few thousand years, ballooning directly from gravitational instabilities. In the protoplanetary disk, when a region of gas and dust becomes too massive, it collapses into a hot, dense core that traps material rapidly, creating a gas giant in a single leap rather than a slow climb. These fast-forming worlds may end up far from their stars, or may migrate inward, quickly disrupting disk structure and preventing other planets from forming nearby. Their speed may leave them with eccentric atmospheres layered with ingredients that never fully mixed. These giants are cosmic shortcuts that change everything around them. They are proof that the universe has both patient plans and impulsive designs. Solar systems can form in the wake of supernovas. When a massive star dies in a supernova, it leaves behind not just destruction but also enrichment. The blast scatters heavy elements into surrounding space, filling clouds with iron, gold, uranium, and other ingredients that cannot form any other way. If that material collapses into new stars, their disks become the cradle for planets, rich in metals and volatile compounds. These planets may begin their lives already seeded with radioactive heat sources, complex chemistry, and high-density cores. The shockwave that once shattered the parent star becomes the spark for new formation, creating a family of worlds that carry within them the memory of cosmic death and rebirth. Our own solar system may be such a descendant, since traces of supernova elements still linger in Earth's rocks. Creation in the cosmos is often a direct child of destruction. We have found evidence of solar systems forming near black holes. Even in the extreme gravity, near a black hole, planets can begin to grow. Stars form in great clouds, and when those clouds happen to lie close to a black hole, the disk around a newborn star may still gather material into spinning lanes of rock, ice, and gas. The gravitational field distorts those lanes, compressing material at some points and thinning it at others, but the process can continue if stability is found. Any planets that do form may orbit a star that itself orbits a black hole, adding layers of motion and tidal stress that stretch or heat their interiors. Yet even here, in one of the most dangerous zones in the universe, the laws of gravity and matter still allow planets to grow. The cosmos does not limit itself to easy places. Some solar systems contain planets too hot for matter to stay solid. On some worlds that orbit exceptionally close to their stars, nothing stays solid on the day side. Rock vaporizes, iron liquefies, and even the crust becomes a bubbling sea of molten minerals. Temperatures can soar to levels hot enough to melt diamond, or strip electrons off atoms, creating an ionized atmosphere, more like the surface of a star than a planet. Material evaporates and rains back down, creating cycles of vapor and condensation driven purely by heat. Winds can transport molten clouds to cooler regions, where they harden into black glass before sliding back into lava. These planets endure a state of continual transformation, where geology becomes vapor and returns again, rewritten every few days. In their extremes, they stretch the definition of a planet, showing that the universe allows not only solid ground and liquid ocean, but worlds full of boiling stone and metal gas. Some planets shed their atmospheres into space. There are planets so close to their stars or so lacking in magnetic protection that their atmospheres do not remain bound to them. The upper layers of gas expand under intense heat and ultraviolet radiation, rising high enough for stellar winds to sweep them away. This creates ghostly streams of hydrogen, helium, or even the escape can occur gradually over billions of years, or dramatically if the star emits powerful flares. Eventually, the atmosphere may thin to nothing, leaving behind an exposed surface, or metallic core that was once hidden under thick clouds. Such planets show that atmospheres are not guaranteed. They are delicate structures held together only by gravity, chemistry, and the constant tug of a nearby star. And even the most complete and complex sky can slowly break apart and vanish into the dark sea of space. There are solar systems with planets made almost entirely of gas. Some planets in the universe are so vast and lightweight that they are little more than oceans of gas held together by gravity. Their layers are made of hydrogen, helium, or less common molecules like methane, and they lack the solid surfaces we associate with Earth. Deep inside pressure compresses these gases into exotic forms of matter, including metallic hydrogen that behaves like a liquid metal and conducts electricity. Above these depths, giant storms swirl endlessly, driven by heat from the planet's interior, or from the distant light of the star it orbits. Clouds thousands of kilometers thick may form and dissolve over centuries, shifting the colors and temperature of the atmosphere. These planets defy the idea that they are dynamos of motion and energy, spheres where air is both the surface and the depths, and change never pauses. Some solar systems contain more than one habitable planet. A few solar systems are blessed with more than one planet in the region, where temperatures allow liquid water to exist. These systems contain multiple Earth-sized bodies orbiting in gentle paths, close enough to share starlight and energy, but far enough apart to avoid gravitational chaos. Each planet may have its own continents, oceans, weather, and atmosphere. One might be rich in volcanic activity, another may be covered in shallow seas, and a third may bear thick cloud layers that slowly rain water upon a stable crust. If life arises on one or more of these planets, the others could offer a nearby destination for exploration or communication. Their skies might hold the glowing arc of a neighboring habitable world, visible every night as a constant reminder of shared origins. These rare systems suggest that life might not be alone, even within a single solar neighborhood. We have found planets that orbit so far out they may never warm enough for life. Some planets orbit their stars at such vast distances that they spend their entire existence in deep cold. Light from the star is as faint as moonlight on Earth, leaving the surface in a state of nearly permanent night. These frozen worlds may have atmospheres, but their gases freeze into the soil, turning the air into frost. Water becomes solid rock, oceans turn into plains of ice, and even the movement of tectonic plates may cease due to the planet's lack of internal heat, with little sunlight to power. Yet these planets still hold secrets such as trapped gases, buried oceans of ammonia, or ancient cores still emitting. the last remnants of heat from formation while uninhabitable. They show us the outermost edge of what a planet can be. Some planets are so dense they must contain more than one core. A handful of exoplanets measure so dense that traditional models of metal and rock cannot explain them. Their mass suggests that they may have formed through the collision and merger of multiple planetary embryos, each carrying its own metallic core. Over time, the cores fused together, while much of the remaining crust and mantle were lost to space in violent debris clouds. Deep inside these worlds, pressure and temperature reach incredible levels, forming strange alloys and crystalline structures unknown on Earth. Their density affects everything from gravity to magnetism. A surface step might feel like a fall, and the pull of the ground would be overwhelming. Compared to what we know, these planets show the scars of cosmic violence, evidence that creation is not always gentle. Sometimes worlds are built out of the shattered remains of others. Solar systems can form with no icy objects at all, while we take ice for granted in our solar system, especially in the outer regions and comet clouds. Not all planetary systems have it. Some form in environments too hot, too crowded, or too turbulent for ice to freeze during formation. Others form around stars that emit high levels of radiation, evaporating frozen elements before planets can gather them. In such systems, all planets are rocky or metallic, with no frozen reservoirs to balance temperatures or deliver water through impacts. The universe writes its stories in endless variations, each solar system a unique expression of cosmic power. Some planets have atmospheres so thin or entirely absent that oceans may never form. Their landscapes are dry, dusty, and scorched. Even when orbiting at safe distances, these barren solar systems challenge our assumptions about how vital ice is to planet formation. They reveal that water, one of Earth's most common ingredients, is not a universal feature of planetary creation. We have discovered planets with weather systems larger than Earth. Some worlds experience storms of unimaginable scale, driven by intense heat, rapid rotation, or thick atmosphere. A single storm may stretch across the planet's entire circumference, with winds traveling thousands of kilometers. In a single cycle, these systems can last for centuries, fueled by planetary internal heat or continuous stellar energy. Lightning may crackle through clouds hundreds of kilometers deep, illuminating the atmosphere like slow-pulsing fire. Jet streams and high-altitude vortices twist around the poles, carrying energy and material in organized, repeating patterns. In these massive weather systems, the concept of a calm day might not exist. The sky is always in motion, wrapping the world in endless change. Some solar systems contain rogue planets that were captured. These wanderers formed in solar systems, but were later ejected into the emptiness between stars. They drift for millions or billions of years, frozen in darkness, until encountering another star's gravity. If the encounter is gentle enough, the rogue planet may be pulled into a new orbit, becoming part of a different solar system. These adopted planets often bear the chemical signature of their original homes, with atmospheres or crusts that differ from native planets. Their orbits may be tilted or stretched, showing clear signs of a history not shared by their new neighbors. Some planets orbit stars too cold to see with the naked eye. Certain stars are so small and cold they emit almost no, yet they can still form fully functioning solar systems. These faint objects, often brown dwarfs or low-mass red dwarfs, glow mostly in infrared wavelengths, invisible to human eyes. Without specialized equipment, they have enough gravity to gather disks. Where planets can form, the worlds orbiting them experience dim skies and low heat, even when very close to their stars. Some solar systems are wrapped in huge clouds of comets. Massive reservoirs of icy fragments extend far beyond These clouds, made of trillions of frozen bodies, are remnants from the chaotic early period of planet formation. They drift far from stellar warmth, locked in long, slow orbits that can take millions of years to complete. Occasionally, a comet's path alters, sending it inward toward the planets. These cometary visitors may deliver water, carbon-rich compounds, or other essential elements to inner worlds. We have detected planets that orbit in polar paths. Most planets orbit around their star's equator, following the original spin of the stellar disk. But a few astonishing planets have been found with orbits so steep they'd practically loop over the star's poles instead of circling like wheels. These planets move like spinning tops, crossing above and below the star's north and south poles. This strange alignment is likely caused by past gravitational upheavals, such as near misses with other planets, or the influence of passing stars. Some solar systems form with no planets at all, while many stars form with swirling disks of gas and dust. Some never manage to make a single world. In these systems, the disk may disperse too quickly, blown apart by strong stellar winds, or evaporated by intense radiation before planetary formation can begin. Other times, the disk may lack the right ingredients, containing too little solid material to gather into rocky or icy bodies. Planets can form in disks with more dust and gas. Most planetary disks contain far more gas, yet some disks have been found with unusually high dust concentrations and very little gas. These dusty disks are likely remnants of violent past events, such as collisions between planetesimals. In such places, planets may form from dry, hard materials, leading to worlds rich in rock and metal, but poor in atmosphere. Some solar systems have planets that orbit far outside their star's gravity. A few planets have been discovered in orbits so distant and slow they raise questions about how tightly the star actually holds them. These planets may circle at distances thousands of times farther than Earth orbits the Sun, taking millions of years to complete one journey around their star. At such distances, the gravitational pull becomes extremely weak, making the planets vulnerable to being nudged out of orbit by passing stars or interstellar clouds. We have found planets that might be artificial in origin among the thousands of exoplanets discovered. A few have raised eyebrows for their strange structure, exact symmetry, or repeating signals that don't match natural processes. Some appear as perfect spheres where chaotic formation should make them uneven, others block starlight in patterned ways, suggesting rings or segments rather than natural globes. Some solar systems contain stars too close together for planets to survive. Binary and multiple star systems are fairly common in the galaxy, but not all allow planets to orbit safely. In some cases, the stars are so close or changed distance so rapidly that no stable region exists for planet formation. Any object caught between them may be torn apart by tidal forces or flung into space at high speed. We have detected solar systems with planets that evaporate over time. There are planets so close to their stars or made of such delicate materials that they are slowly dissolving into space. Their surfaces vaporize under intense heat, and atmospheres expand into wispy trails that stretch behind them like burnt shadows. Some lose more than 1,000 tons of gas every second, shrinking in both mass and radius over time. Some planets are too young to have solid surfaces. Newly formed planets can remain molten for millions of years after birth. The heat from their formation, combined with collision energy and radioactive decay, keeps their surfaces in constant liquid flow. These young worlds may glow faintly in infrared light, like tiny embers cooling in the dark. There are solar systems that are nearly perfectly symmetrical. Some star systems are arranged with almost uncanny order. Planets orbit at precise distances, reflecting balanced ratios. Moons arrange themselves in repeating patterns, and orbital periods lock into harmonious timing that repeats like clockwork. These symmetries are not accidents, but results of long-term gravitational interactions. Some planets have oceans of liquid carbon dioxide. On certain worlds, with the right pressure and temperature, carbon dioxide behaves not as gas or solid, but as a dense flowing liquid that can pool into oceans. These seas may stretch across entire hemispheres, shimmering with frozen fog at the surface, where cold air brushes against the dense fluid below. Volcanoes may release geysers of liquefied carbon dioxide that fall again as freezing rain. We have detected solar systems with planets on million-year orbits. Some planets orbit their stars so slowly that they take more than 1 million Earth years to complete a single revolution. These distant giants travel on paths so wide that their parent star appears no brighter than a brilliant speck in their skies. They feel almost no warmth from starlight, relying instead on internal heat from their formation. Some solar systems have planets too heavy to be made of rock. We have detected planets with densities and masses so great they cannot be composed of ordinary rock or even iron-rich cores. These super-dense planets are thought to contain exotic materials compressed into forms that don't exist naturally on Earth. Planets can form from the remnants of colliding moons. Sometimes planets are not born from single disks of gas and dust, but from shattered moon remains after catastrophic impacts. When two large moons crash together with enough force, they eject clouds of molten rock and debris that can coalesce into entirely new bodies. Over time, solar systems can change shape over billions of years. Planets, stars, and debris don't remain fixed in place forever. Over time, solar systems can stretch, fold, or transform as gravity, stellar evolution, and external influences reshape them. As stars lose mass through radiation, their gravitational pull weakens, allowing planets to drift outward into colder, quieter orbits. Some planets are so puffy they could float in water. A strange class known as superpuffs are so low in density that if a large enough ocean existed, they could theoretically float. These worlds are often similar in size to Jupiter, but contain only a fraction of its mass. Their atmospheres are inflated by heat and low gravity, creating fluffy gas layers extending thousands of kilometers. From their core, we have found planets that orbit so slowly they barely move. Some planets orbit so far from their stars that an entire human civilization could rise and fall. Before the world completes even a tenth of its path, a single orbit may take hundreds of thousands of years or even longer. Some solar systems hide planets behind their stars. There are planets we can only detect intermittently because they orbit in such a way that they remain hidden behind their parent star. We infer their presence from gravitational tugs or faint changes in starlight. There are solar systems with planets that never see their sky. Some planets are covered in such thick cloud layers or atmospheric haze that the sky is permanently obscured. Surfaces are wrapped in darkness or diffuse glow with no stars, no constellations, and no sight of the sun or galaxy beyond. We have detected solar systems forming in binary in some regions of the galaxy. Two stars orbit one another, while planets form around them both. These binary systems create complex gravitational landscapes, influencing dust and gas disks in ways that lead to unusual planetary orbits. Some solar systems have stars that steal planets from each other. In crowded star clusters, close encounters can cause stars to tug planets out of each other's orbits. When two stars pass near one another, their gravity can pull a planet into a new path, stripping it from one star and placing it in orbit around another. Planets can form in disks of pure ice in the coldest regions of space beyond the reach of starlight or heat. Particles of frozen water, methane, and carbon dioxide can collect into disks made almost entirely of ice. These icy rings surround young stars, or even planets forming stable structures where gentle collisions gradually fuse grains into larger chunks. Some solar systems have their own mini black holes. In rare cases, a star may form near the remnants of a long-dead giant, a black hole so small it exerts just enough gravity to sit peacefully within a new solar system. These mini black holes may be relics of ancient explosions or We have found planets that exist only as molten lava. Some planets are located so close to their stars or formed so violently that their entire surfaces remain oceans of molten rock. Temperatures may reach thousands of degrees, hot enough to vaporize metals or turn stone into glowing rivers. These worlds often have no atmosphere since gases cannot condense or remain bound to the surface. Some solar systems may form entirely without water. While water is abundant in our solar system, it's not guaranteed in every planetary nursery. Some stars form in dry regions of interstellar space where hydrogen is plentiful. But oxygen-rich materials are scarce. In such environments, planets may form from dust, metal, carbon, or silicates with almost no ice to deliver water later. Some planets form at the edge of interstellar space. Not all planets form close to warm, bright stars. Some emerge in vast, cold regions at the edges of molecular clouds where starlight is faint, and gravity barely binds the gas and dust. In these distant places, particles collide slowly and gently, sticking together over millions of years without being vaporized by heat. There are solar systems with sunless inner regions. Some stars are surrounded by thick rings of dust or gas that block light from reaching the innermost planets. These planets orbit in permanent twilight, warmed only by faint, indirect radiation or their own formation heat. We have found signs of planets shaped like footballs. Gravity usually shapes planets into near-perfect spheres, but intense tidal forces from a nearby star or massive neighbor can distort a world into an elongated form from a distance. These planets resemble cosmic ovals. Some stars are so enormous they burn through their fuel in just a few million years, yet even in that short time, their surrounding disks can give birth to planets. These solar systems are doomed from the beginning, fated to destruction when the star collapses into a supernova. Some solar systems are so young, they still glow. In their earliest stages, solar systems are illuminated, not just by their stars, but by their own formation heat. Dust, gas, and newborn planets radiate an infrared light, heated by constant collisions and material compression. Even the planets glow softly, lighting their own skies before cooling into darker worlds. The study of solar systems is helping us discover how rare Earth might truly be by comparing hundreds of planetary systems across the galaxy. Scientists are discovering just how unusual Earth may be. Many systems lack rocky planets or contain only hydrogen-helium giants. Others orbit multiple stars, experience intense radiation, or lack key ingredients like water or carbon. Some are too young for life to evolve, and others are so old that any habitable worlds might already be gone. Thank you for drifting through the endless quiet of the cosmos with me tonight. As we wandered together from one solar system to the next, we saw just how strange and beautiful the universe can be. Worlds of ice and fire, stars that share their light across impossible distances, planets that form, dissolve, collide, and begin again. Every system a different story, every orbit a gentle turning of time. If you enjoyed this quiet journey through the stars, I invite you to like, subscribe, or share a thought below. It helps other curious dreamers find their way here, one sleepy soul at a time. But for now, let all that drift away. Let your breathing slow. Let your mind loosen its orbit, floating free like a comet. Through still, silent, dark, the universe will keep turning. Without you for a while, you have done enough for today. Close your eyes, rest, and dream of other skies. Good night.